All right, quadratic surfaces. So we are going to deal with equations rather, that contain terms x, y, z, x squared, y squared, z squared. Um, however, if we shift the graph of an equation, say c units up, the way we achieve that is by changing every z into a z minus c. So that is a shift up by c units. If we want to shift to the right, we change every y into, into y minus b, and that is a shift to the right, b units. And if we want to shift towards us in the positive x direction, oh, I'm assuming a, b, and c are positive numbers. If we want to shift towards us, x in the positive x direction, then we have to change every x into an x minus a. That corresponds to a shift in the positive x-axis direction. Again, we're assuming A, B, C are positive. The reason why I bring that up, well, in addition to knowing, we have to know that anyway, is because if you see an x squared and an x together, that really boils down to an x squared by itself with a shift. By completing the square, we don't really have two terms when you have x squared and x. We really have an x minus a constant squared. And we can see that by completing this square. Let me start out with a simple example, a first example of a quadratic surface. The simplest one, let me start with a new sheet of paper. So let's call this example 1. Is going to be a sphere. If we have the equation x squared plus y squared plus z squared equal to 100, that is a sphere centered at the origin. So sphere with center at 0, 0, 0, and radius 10, because the square root of 100 is 10. So if you look at the picture, you're going to end up with a nice ball. Yeah, it's 10 units each in any one direction, and that's going to be a sphere. Notice, let's elaborate on this equation. Notice that all of those quantities, by virtue of being squared, have to be positive. And all of the three quantities, positive quantities, together have to add up to 100. That means that none of those quantities can exceed 10 or negative 10 in the negative direction. None of them. Let me compare to x plus y plus z equal to 100. This is, as we know well, this is a plane. Yeah, let's just make sure we know, because we're comparing. So you got the x, y, z axis, and then This is 100, this is 100, 100, 100. So it's a large plane, it's way out. And there's the plane, not to be confused with a sphere. But what I wanted to point out is that in this case, z could exceed 100. Z could be 200, no problem. So z would be way up there. But the way to get up to 200 is by compensating with negative x's. So for instance, x could be negative 50, y could be negative 50, plus 200 gives us 100. So way back here and up, we have a point, negative 50, negative 50, 200 that belongs to this plane. We don't see it in this picture, but it's up and back. All right. In contrast, here on the sphere, z cannot exceed, yeah. So in contrast, when we have x squared plus y squared plus z squared equaling 100, z cannot be 200. Not. Because not even 50, not even 20, if not even 20. Because if we square 20, we end up with 400. Yeah, 20 squared would be 400. And those two quantities are positive, have to be positive, at least 0. So there's no way we can add positive numbers to 400 and get 100 back. So we are bound at this equation, again, because those three quantities have to be positive. That means that no one of them can exceed 10 or negative 10 in the negative direction. The magnitude of each one of those quantities has to be less than 10, the absolute value. All right, so that is an important consideration. On a plane, an equation like this, all of those could be any number, 200, a million, just put negative half a million here, negative half a million here. Well, actually, that would have to be 1,100,000, and then negative half a million, negative half a million, and voila, we got a nice point that satisfies this equation. And here, the most any single one that can be is 10. And if this is 10, then there's not even room for any of those to be more than 0. They have to be 0. So that's why when z is 10, we have this point up here, or the same point on the bottom, well, the opposite north and south pole. And that's it. X and y are 0, so those two poles have to be on the z-axis. There's no room for x and y to be any bigger than 0. All right, this is an important consideration as we move on to, well, before I continue though with the ellipsoid, I wanted to show you a shift. Let's call this example 2. Say you have x squared plus 8x plus y squared plus z squared equals 100. We don't want to confuse that with this example. So this is a sphere. This is a little misleading. You may think, one may think that the radius is 100. It isn't, because there's this extra x. So what we do in this case is complete the square, x squared plus 8x plus 16 plus y squared plus z squared equals 116. Now we can factor that as x plus 4, quantity squared, plus y squared plus z squared equals 116. And now we realize that we have the form x squared with a shift, y squared z squared equals 116. So this is a sphere with center at -4, 0, 0, and radius square root of 16, rather square root of 116, 29 times 4. Yeah, so that is the same thing as 2 times the square root of 29. Let me do a quick computation. 29 square root times 2 equals about 10.8. 10.8. So we have a sphere that is centered back here at -4, and radius, well, the radius exceeds, so that's a pretty large sphere. You know, if this is 4, then there's about 6 more units this way because the total radius is 10. So there's a big sphere which is not centered at the origin, it's centered back there. Yeah, so if we have x squared and x, don't worry about what I meant to say is then we actually have a shift. We don't have two different kinds of variables, or it is really the same x squared shifted. Okay, so that is the easiest or simplest one to show, and that is the sphere. Now we're going to move on to the ellipsoid. Oh, before we do the ellipsoid, let me just show you one more thing. One more thing. Okay, if you have x squared plus y squared plus z squared equals 100, we said that z cannot exceed 10 because 10 squared gives us 100, and that's as far as we can go because we have to add on top of that positive numbers. Sometimes it will be convenient to rewrite this as, to divide by 100 and rewrite this as x over 10 squared plus y squared over 10 squared, which is 100, plus z squared over 10 squared. If we divide by 100 and then factor the 100 into 10 squared, then we equal 1. And this is convenient and handy because if we didn't have the tens at the bottom, this will tell us that neither one of those can exceed 1. None of those can exceed 1 in magnitude. If we divide by 10, that means that the ratio cannot exceed 1. And that means that z could go all the way up to 10, because in that case we have a fraction that it is equal to 1. If z is equal to 7 or 8 or 5, that keeps us within 1. The handy thing about this is that we can clearly see how far we can go. The x cannot exceed 10, the y cannot exceed 10, the z cannot exceed 10. All of them are bounded by 10. And this 1 achieves that because, again, if z is smaller than 10, we have a proper fraction, smaller than 1. If z is bigger than 10, then we have an improper fraction, bigger than 1. But that is a problem because then we have more numbers to add to, which will way exceed 1. So this tells us how far we can go. This is even more important. Perhaps it is not so useful when you have a sphere, but let's do an example 3. Let's say you have x squared over 2 squared, which is 4, plus y squared over 3 squared, which is 9, plus z squared equals 4 squared, which is 16. Sometimes this is written simply as x squared over 4 plus y squared over 9 plus z squared over 16, all of them equal to 1. This is a deformed ball. And essentially, we have the same kind of idea. We have positive quantities by virtue of squaring each one of those. And the denominators are different, which means that each one of the variables can only go as far as 4 or 3 or 2. So when we draw a picture of this, we don't have a ball. We have a sort of a ball. We have something that is like an egg, except that it is a little more um, symmetric than an egg. An egg is not totally symmetric. And in which, let's see, the x can only go up to 2, the y can go only up to 3, the z can go up to 4. So we have some kind of egg, yeah, that connects on the bottom and goes back here and goes back there. And these are not circles across, these are ellipses. So we have some kind of knot, except that this is not a cusp. This is very, very smooth all around. So it is completely smooth all over. And again, the interesting thing about this is that it can, about that setup, is that the x can only go up to 2, 3, and well, 2 for the x's, 3 for the y's, and 4 for the z's. So we have a nice, smooth, not a sphere, it's like sort of a stretched sphere so that it's 4 units up and down, but 3 units sideways and only 2 units back and forth. And that is called an ellipsoid. Yep. If, let me change this to a new sheet. If we have a single z, so let's label this as example 4. Equaling x squared over a squared plus y squared over b squared. Well, we know that when, let's put a c under this. If this was 1, we should be familiar with this equation. We would have an ellipse. So in 2D, this is in 3D, but let's compare to 2D. In 2D, if you have x squared over a squared plus y squared over b squared equals 1, we have an ellipse, x-axis, y-axis, this is a, and this is b, a nice, smooth ellipse. We're assuming that C is positive. By the way, C could be negative, but let's assume C is positive. And remember, when we divide a variable by a constant in this kind of equation, what that tells us is how far we can go before we reach 1. So Z, well, this quantity will be 1 when Z matches the value of C. All right. So what this means is there's more considerations before we draw a picture. This quantity is positive, this quantity is positive. If C is positive, that forces Z to be positive, which implies that we have only a graph on the upper half of the space. So there's the three-dimensional space. We have nothing down here if C is positive. Z has to be positive. When Z is equal to C, we have this ellipse, and then it decreases down to this point in an elliptical fashion, this kind of shape, which is the ellipse. On the x-axis, it can go up to A when Z is equal to C. So when the height is C, this is A, this is B, which are not necessarily equal. And the paraboloid keeps growing. This is the basic shape of this paraboloid. It's like a bullet, except that a bullet stops. This continues going up indefinitely. Of particular interest, let's label this as example for A, for B, is when we have a circular paraboloid. So if Z is equal to, in fact, we did this in a previous episode, x squared over 4 plus y squared over 4. That tells us when Z is equal to 1, we have a circle of radius 2. So again, we have a paraboloid as that one up here. The difference is that the cross sections of this paraboloid are ellipses. Yeah, in fact, this is called an elliptic paraboloid in general, while this one would be a circular paraboloid because all the cross sections are circles. So when Z is equal to 1, we have a circle, this is not proportionally correct, of circle of radius 2 across, 2 and 2. And this keeps curving up in the same way. So bigger circles, smaller circles as cross sections. And then this is the origin. So this is the y-axis, x-axis, and the vertical z-axis. So if we have a single z with the same denominator on the x and y squareds, we have this situation. By the way, as an example C, make sure you know how to handle situations where you have, say, x equals y squared plus z squared. This is a circular paraboloid, but we are going in the x direction, or versus also y equals x squared plus z squared. Yep. Again, those are elliptical paraboloids, although more narrowly, those are circular paraboloids. I just call them paraboloids. So that is example 4. Example 5, or the kind of quadratic surface. This one is a tricky one to draw. We have the hyperbolic paraboloid and hyperbolic paraboloid. So first, let's recall paraboloids, rather hyperbolas in general. So let's recall hyperbolas in 2D. So if we have 1 equals x squared over a squared minus y squared over b squared, then we have a horizontal hyperbola. It kind of looks like this. So 2 branches make a horizontal hyperbola. And this distance is, if the center is the origin, and then we go A in each direction, and then B is used to figure out the asymptotes. We have straight asymptotes. By the way, hyperbolas are not 2 parabolas facing each other because the parabola keeps curving. So if you zoom out on a parabola, you always see a parabola. If you zoom out on a hyperbola, if you zoom out far enough, you will see an X. You see 2 lines because the curves get close to the asymptotes, and the asymptotes are straight lines. Yeah. If you have -1 equals x squared over a squared minus y squared over b squared. So in effect, what we are doing is putting y squared minus x squared. If we multiply the whole thing by -1, then we have a vertical hyperbola. So this is a 2D. By the time we get to 3D, back to 3D, we will have z over c, and remember this allows us to stretch z, to stretch things vertically. This is a vertical stretch, essentially, equals x squared over a squared minus y squared over b squared. So what this does is when z is c, this becomes 1. We have a horizontal hyperbola. So we have something that looks like this floating up here at 1. But when z is negative, this kind of situation, then we have a vertical hyperbola. So this is down under the, so this is down to -1, and this is up to +1. But then we go through 0 in a smooth way. So this is the kind of shape we encounter. This keeps going down, down this way. This keeps going up. So if you search, whoops, this was off focus, sorry about that. If you search for hyperbolic paraboloids, you will be able to see this kind of shape. And my best description is that it looks a little bit like the crotch of jeans. You know, on one side, they curve one way, but then by the legs, it curves differently, because that's how it is. That's how it works. The legs come off, but then our front comes up this way. The belly area comes this way. So it curves one way. This graph is concave up if we look at it this way, but if we look at it from another angle, it is concave down. Yep. A and B tells us the ratio in which this curves open. So they could be very, very open or very, very narrow. So yeah, this is particularly difficult to draw, again, because this goes down and then this is, yeah. Well, I would strongly advise you to check pictures. I don't want to use printed pictures in these examples. Example 6. Cones. The difference between a hyperbolic paraboloid and a cone is that now we have a z squared over c squared equals x squared over a squared plus y squared over b squared. Not to be confused with z over c, assuming c is positive. Assume c is greater than 0, equals x squared over a squared plus y squared over b squared. Here, I suppose it doesn't matter what a is, because if it is negative, when we square it, we end up with a positive number anyhow. Oh, I'm missing the square root here. Yep. So those two may seem to be the same, but they're not, because if I really wanted them to be the same, we would have a plus minus, which implies that there's two parts to this. This is a cone, like so. We got the z-axis, y-axis, x-axis. When z is equal to c, so when we have a height of c units from the floor, then this is not a circle, it is an ellipse. In the x direction, we go a units. On the y direction, we go b units, whatever they are. Yep. Yeah. This goes back a unit, so by the time it crosses over to here, we have the same situation down here. So on the x direction from the center, we go a units. On the y direction, we go b units, assuming that this distance is c, we're going down to negative c. Yeah. Yeah. Let's write the cone again. So a cone, z squared over c squared equals x squared over a squared plus y squared over b squared. So the cone has a waist of 0. Yeah. So it opens nicely like a regular cone. And here we have a very, very tiny waist and of radius 0. It's not a circle, by the way, it would be an ellipse, but still its radius is 0. This deforms down to a point. Yeah, the reason why I have to emphasize that is because if we add 1 to this z squared over c squared, then we have our next example, example 7. So if we have z squared over c squared plus 1 equals x squared over a squared plus y squared over b squared, this means that when z is equal to 0, so this portion vanishes, we have at least an ellipse to start with. So if this is gone, we have an ellipse already. So that increases the waist of this cone. So it creates sort of a cone. So instead of having a point here, we have an ellipse. Yep. And we have more ellipses going up and going down. And furthermore, this shape is a hyperbola. Because of that, we call that hyperboloid. Would call it elliptic hyperboloid. Hyperboloid of one sheet. Yeah. So it is nice to know how it is built. It comes from a cone where the radius, radii, increases. It's not one radius because those are not circles, these are ellipses. So they're ovals. But nonetheless, their size increases at the waist, and not only that, that also deforms this shape. Instead of being straight as a cone, the side of this hyperboloid curves. So I'm going to try to squeeze example 8 if I can here. What happens if we decrease z squared over c squared minus 1 instead? If we decrease the waist, that means that there is no waist. So it's not even, we cannot even have 0 as in this case. We have, in this case, more than 0, and in this case, less than 0, so nothing. We cannot start building any kind of graph until we have at least c units. Then we have a waist of 0. So that what actually that does is this sort of squeezes this down to nothing and separates this into 2 portions. So we end up with upper, and this is smoothly curved lower. I'm trying to make them a little bit like a V because as a hyperboloid, this has a straight asymptote, and so does this. So we got two cups facing each other. Neither one is a paraboloid. They are hyperbolas. It's a hyperbola shape. On top of that, the top, a cross section of this is not a circle. It would be an ellipse, and so is this one. And down here in this example, in the hyperboloid, we have this ellipse as a cross section once the height becomes c, and the same thing on the other side. Here, we don't even start. Let's see. Yeah, we don't even start with the shape until we reach c units. So the bottom of this is c units from the xy plane to get to here. Analyze those 8 shapes, go over them, explain to yourself why they are the way they are. Well, a question I have for the viewer is, why is this straight? What suggests in this equation that we should have a straight line? That's a good thing to ask to yourself. So why is this straight? All the other ones are curvy, but that one happens to have a straight side. So that is a good question to ask. And with that, we finished quadratic surfaces.